Hi everyone, welcome back to another lecture on Aero 320, Fundamentals of Dynamics and Control. In today's lecture, we're going to cover a few important topics related to control. We're going to revisit feedback systems. We'll walk through a quick introduction of them, talk about when feedback systems can be stable and what the response of a feedback system is to different input signals. And then we'll move on to a very important theorem called as the final value theorem. This is a theorem that will help us figure out what the final state of the system are as a function of time. And then we're also going to get into some form of common control systems. We're specifically going to look at P, PD, and PID control. These stands for proportional control and proportional derivative control, proportional integral derivative control. And then towards the very end, we're also going to get introduced into the concept of block diagrams. What block diagrams do is they basically simplify complex system transfer functions into easily understandable visual sections, which we would then analyze to create one single transfer function for the entire system instead of having traditional smaller blocks. All right. As a quick recap, we'll start with the typical feedback system. Last class, we were talking about what a typical feedback system looks like. We have a quick block diagram as shown on the screen. Here, the signal R of S, as we discussed last time, R of S stands for the reference signal. This is the signal or this is the input that we typically want to establish the state of our system to be in. A good example for this is imagine you're at a cruise altitude at an aircraft and you now want to start pitching by 5 degrees. Then the reference signal R of S to the signal or to the system should say that it's 5 degrees. So this is the state of the system that you wish for it to take. And then we have the main block called as g of s. This is the main transfer function of the entire system. This is also called as the plant. This basically consists of all the dynamics of the system. And then we have another block called d of s, which represents the control input that we provide for the system. This can be any form of controller. This can be P, PD, PID, any one of those forms. The idea here is that if you want to pitch a space aircraft by 5 degrees, then you provide a reference signal to the aircraft indicating that you want to pitch it up by 5 degrees. This is then followed by some amount of control mechanism, and this control mechanism would then cause the ailerons to deflect by a certain angle, which would then cause the aircraft to pitch. So this block D of S is basically the avionics section within an aircraft, which is going to tell it how much of deflection is required on its ailerons. All right, and then we have WD. We discussed WD to be some form of disturbance noise. This is usually caused within the system itself. As you provide a control input to the system, there can be some amount of noise that gets added, and we model this as disturbance noise. Uh, and then once the signal has been sent into the system, the aircraft would now start pitching. Then the output of the aircraft system Y, this is the actual pitch that we measure using different sensors on the aircraft. So this would be the output of the aircraft. So let's say we provide a reference signal of 5 degree for pitch. This passes through the block D of S, which is basically the avionics section. This sends a command for the aircraft to change its control surface deflections, and which in turn passes through the dynamics of the aircraft to generate an output, which in our case is going to be the pitch. But let's say we start doing that, and then the aircraft is currently only at 1 degree of pitch. Then this output basically passes back to the input. As we're measuring the final output, there is some amount of noise that gets added, which is given by Wn of S. This is basically any amount of noise that is present within the sensor. This information now goes back here, and this gets cancelled with the reference signal, which was originally 5 degrees, and now we said the pitch was about 1 degree. So the amount of pitch that the aircraft should still perform is about 4 degree. We call this 4 degree as an error signal, which is given by E of S. E of here, S stands here for error. This is the desired state of the system given by R of S minus the current state of the system, which is Y of S. So the error signal here is basically the difference between the desired state we want our system to be in versus the current state it is in. And this feedback loop keeps going on until the aircraft reaches 5 degrees of pitch. Then at that point, our Y of S is 5 degrees, our R of S is 5 degrees. Then our total error signal, which is basically the difference between R of S minus Y of S. Once the output of the system reaches 5 degrees, they cancel out each other and we provide a zero input to the control, or in other cases, the aircraft just holds its current state. All right. And then we also looked at what an ideal feedback system is. An ideal feedback system is any system where we are assuming that there are no noises added to the system. Then in such a case, we looked at what the transfer functions for the systems are. Again, I want to remind you here, R of S is the reference signal to the system. Y of S is the output of the system. Then the error signal that passes into the system is given by R of S minus Y of S. And the total transfer function is nothing but the response of the system to any input that we provide. And in this case, the transfer function TF is given by uh, is is given by G of S times D of S divided by 1 plus D of S G of S. This is nothing but a transfer function, which is nothing but output by input. All right. And if we assume, if we provide a step input, then R of S in this case becomes a 1, or in other words, the output of the system for an input step is nothing but G of S times D of S divided by 1 plus D of S times G of S. So if you provide a step input to the system, then the output of the system is given as the same as the transfer function itself. All right. And now what we're going to do is we're going to analyze how stable these feedback control systems are going to be. In the last class, we spoke about how a typical second order system's transfer function can be represented as. So, reminding you guys about the typical transfer function once again. A typical transfer function of the second order system, in our case, we took a simple mass spring damper system, is given by the equations as you guys see on the screen. Here we said when we set the numerator is equal to 0, then the roots of the equations of the numerator tells us the number of zeros in the system, and when we set the denominator is equal to 0, that tells us the poles of the system. One key definition that we're going to walk through right now is the definition of a characteristic equation. Characteristic equation is nothing but the equation on the denominator of the system for the specific second order system, which is given by s squared 2 times zeta omega n times s plus omega n squared. Here, the roots of the system, which basically corresponds to the poles, are given by this equation you guys see right here. Taking a quadratic equation, if you want to solve for the roots, this is something we all know from high school, which is given by negative b plus or minus b square minus 4ac divided by 2a. Just plugging into that equation, we get the two roots for the system given by s. Here we're going to define two new constants. One is called as the time constant, which we're going to define as negative zeta times omega n. This determines how long the system takes to respond to a specific input. And then we're also going to define another quantity called as the damping frequency, which is given by omega n times square root of 1 minus zeta squared. Here, notice that the damping frequency is a function of the natural frequency of the system, or in other words, the damping frequency is going to tell us how long the system is going to oscillate around the state before it settles down. A good example for this is, let's go back to an aircraft pitch controller. Here, let's assume your aircraft is currently at 0 degree pitch, and you provide a control input to your aircraft saying that you want to pitch up by 5 degrees. So your reference signal becomes 5. This then passes into the control unit, which then generates some amount of control, which is a deflection on the control surfaces in the aircraft. This then starts to generate some amount of pitch. And this keeps going on in the feedback loop until 5 degree in the aircraft is achieved. And we basically have some amount of control over how fast this aircraft settles into this final pitch state of about 5 degrees. And we also have some amount of control in how long the aircraft is going to take in order to achieve this, along with the number of oscillations we're going to see in a system. We're going to dig a little deeper into that in just a second. But before we even get there, I wanted to give you guys some definition about stability. The stability of the system, like you guys already know, is the ability of the system to attain a certain state that we're looking at, or in particular case, we're going to look at the equilibrium state. For a typical second order system, if the time constant omega is um, is less than zero, then plotting the omega and the sigma of the system on this new plot, which we call as sigma j omega plot, which is what it's commonly called as, or some people also like to call it S and J omega plot. Here, basically, we solve for the characteristic equation of the system and then plot the poles and zeros of the system on this. If the poles and zeros of the system are on the left-hand side of this plot, so basically, if it is in quadrant 2 or quadrant 3, then the system is said to be stable. If the poles of the system are on the right hand plane of the j omega axis, then which is basically in quadrant 1 or quadrant 4, then the system is said to be unstable. All right. Now, what happens if the poles of the zeros exactly lie on the j omega axis? Then, if they lie exactly on the j omega axis, we call them marginally stable systems. Okay. So here, the two key parameters that is going to define the stability of the system is given by the roots of the characteristic equations, or in other terms, the denominator of the transfer function mainly determines whether the system is going to be stable or unstable. We looked at two new constants called as the time constant and the damping frequency. Here the time constant sigma basically tells us uh, how long the system takes to decay and settle to the final state. This is called as decay rate of the system, and omega here, or in other words omega d, determines the number of oscillations or frequency in the response of the system before it settles to the final state. So I'll write it as oscillatory motion. Oscillatory frequency. Okay, awesome. Now, let's assume we have a typical second order system and we find the roots of the characteristic equation. So it basically tells us where the poles of the system lie. And let us assume that the poles are given by the solution for the characteristic equation, which in our case here, we said the solution for the system S is given as this equation, or substituting the definitions that we just had, then S is given by sigma plus or minus j omega d. So if we know the sigma value as well as the omega d, which is the decay rate and the time constant and the damping frequency, then we can determine whether the system is stable or not. And here, looking at what the time constant and damping frequency depend on, they depend on the damping coefficient zeta, and they also depend on the natural frequency of the system, which is given by omega n. Now, let us assume there is a system where the zeta value is greater than 1. If zeta value is greater than 1, then this S is equal to sigma plus or minus j omega d corresponds to values such that the poles of the system, or the values of S, end up lying on the real axis. The real axis is the axis which has the sigma, and the imaginary axis is the axis that has j omega. Then the poles of the system in this case become real and distinct, or in other words, when we provide any amount of input to the system, then the system does not end up having oscillations and it smoothly settles into the final state. On the other hand, if the damping coefficient is between 0 and 1, then the poles of the system end up lying as a complex conjugate on the sigma j omega plot. So the poles of the system look something like this. Then the system now starts to exhibit some amount of oscillation as it settles down into the final state. So the response of the system will start to look like this. And such a system is also called as undamped system, because once you provide a control input, the system takes some amount of time and creates some amount of oscillation before it ends up in its final state. While in the first case, when zeta is greater than 1, we say that the system is overdamped, where we're providing a lot of control for a lot of control for the time constant, and the damping coefficient or the damping frequency of the system, which causes it to settle smoothly. The disadvantage in the overdamped system is the fact that the system now settles to the final state much faster, but then uh, um, all right. And then moving on to the third type of value for zeta. If zeta is equal to 1, then in such a case, the poles of the system end up becoming real and repeated. Or in other words, we would have, if zeta is equal to 1, then we'll have two poles where S is given by negative omega n. This is all plugging zeta into these values, into the S equation and omega d equation. Then in such a case, the system does not end up having any oscillation, and the system is said to be critically damped, where the system smoothly goes to the final state that we desire. And then the last state is if zeta is equal to 0. If zeta is equal to 0, then the poles become completely imaginary. The poles are no longer real, which means to say the poles sit on the j omega axis. And then the final state of the system ends up being a sustained oscillation as shown here, or the system never actually settles to the final state. So here we spoke about four different types of zeta value. One, when zeta is greater than 1, then the poles of the system end up being real and distinct. In such a case, the system is stable because both the poles are on the left-hand plane of the sigma j omega plot, and the system smoothly settles into the final state. In the second case, we said if zeta is between 0 and 1, then the system's pole end up being complex conjugate numbers, and then this results in a stable system again, except it takes some amount of time or some amount of oscillation before it decays. And then there is a critically damped system. Critically damped system is a system where zeta is equal to 1. Here the poles of the system become real and repeated, which means they have no imaginary component. They're still on the left hand side of the on the left hand plane of the sigma j omega plot, which means the system is still stable, and then there is no oscillation. And then the last case is when sigma is equal to 0, or if zeta is equal to 0. If zeta becomes equal to 0, then the real poles disappear, then all the poles of the equation end up becoming complex numbers, and they lie on the j omega axis. What this means is that the system is now marginally stable, which means the system state will no longer explode, or the system state will no longer settle down into a final value. It is somewhere in between, or the system starts to oscillate around the desired condition. What this might look like is, let's take the aircraft example again. If you provide a pitch input of 5 degrees and you've chosen a zeta value to be 0, then basically your aircraft would, rather than settling at 5 degrees of pitch, it will start to oscillate somewhere between 4.5 degrees to 5.5 degrees, and it would never actually settle at the 5-degree pitch that you desired. And often marginally stable systems are undesired because we want the system to stay to reach a stable state. which is why oftentimes we end up choosing a zeta value between 0 and 1. When zeta is greater than 1, system becomes overdamped and it settles faster. And when zeta is equal to 0, I mean, when zeta is equal to 1, then the system becomes critically damped. It takes some amount of time before it settles to the final state. Or when zeta is between 0 and 1, then the system becomes underdamped, or it takes a long amount of time before it settles to the desired state. All right. Now let's look at what each of these zeta values actually look like for the output of the system. Let us say we provide an input of 5 degrees of pitch for an aircraft, and you want the aircraft to finally settle at a pitch of 5 degrees. So then I'm going to say the desired amount of output that we're looking at for an aircraft pitch control here is going to be somewhere around 5 degrees. This is the point where we want the aircraft to settle at some amount of time t0, we start to add a control input, which is basically telling the aircraft we need to pitch up by 5 degrees. In the first case, if we choose a zeta value, to be between 0 and 1, then the system becomes underdamped, or in other words, the system's response or the pitch of the aircraft starts to change like this with time, and then it slowly settles down to about 5 degrees after some amount of time. This is for cases when we choose 0 and less than zeta less than 1. If we choose any zeta value that's between 0 and 1. Now, if we choose zeta is equal to 1, then the system becomes critically damped. In this case, as you provide the control input, the state of the aircraft ends up going like this, where we have zeta is equal to 1. Such a system is called critically damped. Here we no longer see these oscillations within the system, or in other words, the aircraft state will never actually go more than 5 degrees of pitch. It'll try to smoothly transition from 0 degree pitch to 5 degree pitch. And then the last case, when zeta is greater than 1, then in such a case, this is a case where we're trying to be more cautious with the system. We're trying to kill all and any oscillations possible for the aircraft. Then in such a case, the pitch of the aircraft will look something similar to the pitch of the aircraft will look something similar to this, where the aircraft is overdamped, so there is no oscillation, and the aircraft settles at a final pitch value of about 5 degrees. So now what this is telling us is, by choosing the value of zeta, the response of the system starts to change. Or in other words, we now have control over how long the system can take before reaching a desired state, and how the system also reaches the desired state. It could either have some oscillations, it can have no oscillations, or it can completely prevent oscillations by being an overdamped system. So let me write it down here. This is when zeta is greater than 1. All right. So this gives us some amount of control or flexibility for control system designers to come up with how they want to control the aircraft. A good example here is that, let's say you are trying to design a control system for a fighter jet, right? For a fighter jet, you want the aircraft to settle into its final state much faster, but you are okay to allow the aircraft to have some amount of oscillation. Say, for example, a fighter jet, you want to pitch 5 degrees, then a desired response for a fighter jet where y of t is the pitch angle and t is the time. You are okay for it to overshoot than 5, but then settle at 5 much faster, right? But for a typical passenger aircraft, because you look at more comfort than how fast the aircraft actually pitches at 5 degree, you might be looking at a critically damped or an over damped system, where you want the pitch of the aircraft to be as smooth as possible before it reaches a desired pitch of say 5 degrees. While that for a fighter jet now can be that the pilot is okay to experience a little overshoot and undershoot, where he's okay for the aircraft to go somewhere between 5.2 degrees degrees, come back to 4.9 before it settles to 5 degree. The advantage here is that in this case, it might settle down into 5 degrees much faster at a time interval of delta t1, while that in a passenger aircraft you prioritize comfort, so the amount of time it takes for the system to reach the desired pitch might be longer. So based on this gives some amount of flexibility and control for the control system designers to come up with new designs for the control system. All right, so now let's actually dive a little deeper into this to understand how long the system actually takes to reach the desired state once we start providing input. A good representation, good visual representation of what the response of the system is when you provide some amount of input to it is as shown on the screen. This is also called as transient response because the system takes some amount of time before it reaches your desired state. Let's say you want an aircraft to pitch by 5 degrees. The instant you provide a control input saying that, hey, pitch by 5 degrees, your aircraft is not going to be in 5 degrees. It takes some amount of time for the aircraft to slowly pitch up and reach 5 degree, right? So there is some amount of transition time that the aircraft takes to go from state 1 to state 2. And that is why this response is called as a transient response. This basically tells us how long it takes for the system to go to the desired state once you provide a reference signal. And here we're going to define 4 key properties. The first property is called as the rise time. Rise time is basically the amount of time the system takes to reach 90% of the desired signal value. So rise time here is this time given by TR, and TR, or the rise time, is given by pi minus beta divided by omega d. Here beta is basically tan inverse of square root of 1 minus zeta squared divided by zeta. So the rise time depends on the amount of damping coefficient and also depends on the damping frequency, while that of the peak time is defined as the amount of time the system takes to reach the peak value. Peak value is basically the point where the output of the signal is the highest value. So let's say I design a control system for an aircraft pitch control and I provide an input of reference signal of 5 degree because I want to achieve 5 degree pitch, and I have a control system designed in a way such that it slightly overshoots. Then the maximum value of pitch that the aircraft would have before it settles down at 5 degree, that is called as the peak value, and the amount of time it takes to reach the peak time to reach the peak value is given by peak time. This is given by pi divided by omega d. And then another important quantity is called as maximum overshoot. Maximum overshoot is basically the percentage of overshoot that is present within the system. In this case, let's assume that we wanted to have a pitch of about 1 degree. Then let's say the aircraft pitched up to 1.5 degrees and then it came down to 1 degree. Then here the overshoot is given by the difference between 1.5 and 1, and and represented in percentages. This is called as the maximum overshoot. It is given by this equation MP as you see on the screen. And then the last quantity we're going to discuss is something called as settling time. Settling time is basically the amount of time your system takes to start from the time instant where you provide control. In our case, it's at time t0, and until it reaches the desired state of the system, which is the instant where the aircraft's pitch now, let's say, becomes 5 degree or 1 degree based on our reference signal. Then this amount of time where the system first starts to settle, which usually in practical cases is taken as, let's say you want to reach a desired state of 1 degree of pitch, you allow an error margin of about 2%. So if you're reaching somewhere about 0.98 degrees of pitch, then the first instant where you reach that 0.98 degree and you start to settle there is called as the settling time, which is given by TS, which is given on the equation on the screen. It can also be simplified to about 4.4 divided by zeta omega n. And this is for a typical second order system. The settling time can be approximated as this. All right. So now what we're going to do is we're going to assume we have a system and we know the natural frequency of the system, and we're going to pick a zeta value, and we're basically going to analyze how long the system takes to rise to a specific time and what is the time it takes to reach the peak value, and then we're also going to find out what is the maximum overshoot. All right, so just plugging this into an example. Consider you have a second order system which has a transfer function given as shown on the screen. Now let us assume the natural frequency of the system is given by 5 radians a second, and then it has a damping ratio of 0.6. Then we are expected to calculate the rise time, the peak time, and the maximum overshoot. All right. So first let's find out the transfer function of the system, where transfer function of the system is given by typically, if it's I've put it on the screen here, but typically transfer function for a second order system is given by omega n squared divided by s squared plus 2 zeta omega n times s plus omega n squared. Here in the problem, they said we have omega n as 5 radians per second, and they've given zeta value to be 0.6. So these two are given in our problem. Plugging these two values into the standard form of the second order transfer function, we obtain this transfer function as shown here on the screen. Now we are expected to find what the rise time is, peak time is, and the maximum overshoot. Before we go ahead to find that, let's first find out what the values of sigma and omega d are. Sigma, we said, is defined as omega n times zeta, which is substituting in this case is about 3. And the damping frequency omega d is given by omega n times square root of 1 minus zeta squared, which substituting the values in this case is about 4. All right. Now to find the rise time, this is the amount of time the system takes to reach 90% of the desired system state. The rise time is given by the formula above, where we said rise time is pi minus beta divided by omega d. So substituting that, we get t of the rise time is given by pi minus beta divided by omega d. This is pi minus tan inverse of 1 minus zeta squared divided by zeta. Substituting that, we get square root of 1 minus zeta squared divided by zeta whole divided by omega d. Substituting the value for omega d and the value for zeta as seen here, we get a total rise time of about 0.5733 seconds. All right. Then it's asking us to find what is the peak time. Peak time is given by peak time is Tp is given by pi by omega d. Substituting that, we get about 0.785 seconds. And then the question also asks us to find what is the maximum overshoot, which is a simple plug and chug, which is max overshoot, where MP is given by e raised to negative pi zeta divided by square root of 1 minus zeta squared. Substituting this into 100%, basically we end up getting MP 0.095 into 100%, where MP is 9.5%. All right. Now, the next thing we're going to talk about is this very important theorem called as the final value theorem. To give you guys a quick context about it, so far we looked at a second order system where based on zeta and based on the sigma and the omega d values, the system responds in a different way. For example, here in this case, we looked at choosing various values of zeta that basically causes the system to be stable or unstable, and how the system responds over a function of time. So going back into this, looking at this system, we say that if the system has poles in the right hand side of the j omega axis, then the system is basically unstable, or the system will never settle to the final state. While if the system has poles on the imaginary axis, if it has poles, which is the case of zeta is equal to 0, if it has poles on the imaginary axis, then the system tends to oscillate around a certain state and never reach the final target. And such a system is called marginally stable. While if zeta is anywhere between 0 and 1, then we say the system is said to be either overdamped or underdamped or critically damped based on the zeta value. Then in such a case, we just saw that the system is always going to settle into some specified or desired final state. Then what final value theorem says is that if a system has a zeta between 0 and 1, then in such a case, we are able to determine what is the state of the system as time tends to infinity. All right, so the final value theorem tells you that if the system only has poles on the left-hand plane, which means the system has to be stable, and if one of the pole is at origin, then there is a constant steady state value for the output of the system. Then in such a case, the final value theorem tells us as time tends to infinity, then we can estimate what the final state of the system is going to be, or in other words, what is going to be the steady state of the system as the system tends towards its stable final state. This is given by limit of s times y of s as s tends to infinity. What this really means is that it's a powerful tool where if you have some system where you're analyzing the output y of t as a function of time, then if zeta is between 0 and 1, then the state of the system is always going to be oscillating until it settles to the final time, right? So here, as time tends to infinity, these values of states that the system is going to take, which is y of t as t tends to infinity, that is given by the final value theorem, which says this is the same as the limit of s times y of s as s tends to 0. So let's look at a quick example to see what this really means. Consider a simple signal, a simple system where the output y of s is given by this equation on the screen. First, we want to verify if the system is stable and it has poles on the left-hand side. So let us solve for the roots of this equation. To solve for the roots of this equation, we start with the characteristic equation. Characteristic equation in this case is given by s times s square plus 2s plus 10 is equal to 0. Then solving for the roots, we get the roots of the equation are either s is equal to 0 or and s is equal to -2 plus or minus j root 3. Then in such a case, we see we have one root at origin or one pole at origin, and the other two poles are on the left-hand side. Let's verify that. If this is the sigma and j omega, we see sigma as -2, and here we see omega d is root 3. Then in such a case, the poles of the system are at -2, negative j root 3, and we have -2 positive j root 3, and we have one pole at the origin where we have 0 comma 0. Then this system qualifies to apply final value theorem. And now, as we provide some input to the system will now start to behave in such a way such that the final state y starts to oscillate before it settles to its final value. And this final value is given by y of ss, or in other words, we're going to call it y steady state is the state what the system settles at. Then by the final value theorem, we can say limit of y of t as t tends to infinity, which is the y steady state, is given by limit of s tends to 0 of s times y of s. This is nothing but s times y of s, which is 5 of s plus 1 divided by s times s squared plus 2s plus 10. Substituting this, we'll cancel s and s. This is nothing but 5 times s plus 1 divided by s squared plus 2s plus 10. As s tends to 0, this is basically this basically ends up being in the as s tends to 0. So in the numerator, we get 5, and in the denominator, we end up getting this would be 0 squared plus 0 plus 10. This would be 5 by 10, or we get 1 by 2. So the steady state of the system will settle at a value of 1 by 2. Now, let's look at what happens if the system's equation was given by y of s is 5 times s plus 1 divided by s times s square minus 2s plus 10. Now, in such a case, I want you guys to go ahead and find out what the roots of the equations are and then plot them into the j omega axis and sigma axis. Here, you will notice the roots of the equation are s is equal to 0, and then I want you to find what the other root of the equation is. The other root of equation is given by s is equal to minus b, which is 2, plus or minus square root of uh, b squared, which is 4 minus 4ac. 4 times 10 is 40, divided by 2 times a is 1. This is about negative 2 plus or minus square root of negative 36 divided by 2. So the other roots are 0, comma, s is equal to minus b. So this will be positive 2 here. Sorry. This will be 1 plus or minus j roots j 6, because square root of 36 is 6. Then the poles of the equation in this case are one is at 0 comma 0, and the other two poles are at 1 plus j 1 plus 6j, which is 1 plus 6j, and then we have 1 minus 6j. In this case, the poles of the equation stay on the right hand side of the on the right hand plane of the j omega axis, or in other terms, the system is unstable. For an unstable system, we know that the system will never settle into a final steady state. In such a case, we cannot apply the final value theorem. All right. Now we will move on to the more interesting aspect of the course, where we're going to talk about the different types of control systems. And this is what I want you guys to focus on your project as well, where we're going to talk about the various types of control and how we're going to apply it to control a specific system. All right. There are three common types of control that we're going to learn. The first type of control is called as a proportional control. This is a type of control system where your control input d of s is nothing but some constant value given by Kp. Or in other terms, your control input U is nothing but some Kp times the error signal. Here, error signal is E of t. Here, we're going to call this the control input. Here, we're going to call this U of s. If we write it in time domain, the control input is nothing but U of t. Then the error signal E of s in time domain is nothing but E of t. Then in such a case, we say that for a second order system, if we provide some amount of proportional control, then this is as good as the system acting as though it has a spring attached to it. All right. And the effect is very similar to the effects of the spring in a mass spring damper system. This provides direct correction to the error based on the size of the input. Or in other terms, think about a reference signal. Let's say I'm going to go back to the aircraft example. I want to pitch an aircraft to 5 degrees. Initially, we don't have any output. Then coming here, the error signal will be 5 degrees. This gets multiplied by some constant Kp. Then our U of s will be Kp times 5 degrees. This then goes into our input, and let's say This finally gets tracked into an output of about 4 degrees. Then coming back here the second time, we have 5 minus 4, which would be 1 degree here. Then 1 gets multiplied by some constant kp. Then this will be 1 times kp. This goes here. And then let's say this time it's 5. And 5 minus 5 here, this time becomes 0. Then we have 0 degree. Then we have 0 control input. And then the system settles at 5 degrees of pitch. What you're noticing here is every time you provide some amount of input to the system, that gets multiplied by some value or some scalar value of kp. Which means to say that based on the error that is present within your system, the error gets scaled up if you have higher error. Or in other terms, if you have some error E of S, then this looks as if it is Kp times E of S in the output of your control system. Which means to say, as your error in the system increases, the amount of control that you provide also increases. This is sometimes undesired. Let's say you're using it for aircraft pitch control, and then you provide a pitch of 5 degree, but then your aircraft only generated a pitch of about 1 degree. Then the difference between them is 4 degrees, right? Now this 4 degree gets multiplied by a constant kp, which usually is a very large value, sometimes of the order of the order of 1e6 or 1e5. Then a large amount of control signal then enters your system, causing large deflections on your ailerons. Or in other words, what this ends up doing is that if you have a system and initially there is high error, then the system tends to oscillate too much before it settles to the final state. The higher your error is, the higher is going to be your control input. Or in other terms, in our case, it's going to be higher the deflection on the control surfaces of an aircraft. This is usually undesired if you're designing a control system for a passenger aircraft where you don't want to have a lot of oscillation and you want it to be a smooth, steady flight as much as possible. So one of the downsides of this method is that it has large errors, and to compensate large errors, you need large amount of control. And a limitation of this method is that it cannot fix any steady state error. Let's say after some amount of time, your aircraft, instead of settling at 5 degree, it settles at 4.99 degree. Then your control system is always going to keep generating some amount of control because your aircraft state settled down at 4.9. Or in other words, what ends up happening in reality is that your aircraft state will never settle to 5 degree. It'll oscillate, except the oscillations are going to be very small here. All right. But this is quite useful if you're using it for simple use cases. For example, if you have a simple basic motor and you just want to control the speed of the motor, this is a great use. The reason for this is because you're using a simple system. You don't want to complicate the control. So using a simple proportional control works. Now, the next type of control system we're going to talk about is called as the proportional derivative control, where the control signal is some proportional times the error plus some derivative constant kd times the rate of change of error. So here, this is adding the second layer of control. In the first case, we said higher the error signal, higher is going to be our control input. In this case, apart from just the system scaling down to scaling based on the error present in the system, it's also going to scale based on how rapidly the error changes with time. So if the error signal increases fast with time, then this generates more control input to counteract that increase in the rate of change of error. So the advantage that this gives us is based on how quickly the system's error grows, the control responds to it by creating a control action that's going to keep track of this quickly changing error, thereby trying to bring it to stability. One advantage of this method is that compared to the proportional control, it reduces the amount of overshoot, because overshoot is basically caused due to a swift change in the input of a swift change in the error signal. Then as the error signal changes rapidly, a control input kd scales it accordingly, which causes the system to have an improved stability. But one downside of this system again is that it cannot eliminate steady state error, or in other words, if your system does not settle at a final value of, let's say, you want 5 degrees of pitch and it settles at 4.9, the PD controller can never eliminate that tiny error and actually have the system settled at 5 degrees. And this is a good use case, typically in robotic arm. A lot of robotic arm systems for robots that we use in daily life, especially like those that you guys see with your Roombas. These are the speedy controller is simple enough to implement, cheap to implement, and where we don't really care about the overshoot if we're crashing against the wall, for example, as the Roomba moves, we don't really care. So this is a good example for a PD control. And then the last type of control that we're going to talk about is the PID control. Seems like I have the name incorrect here. So I'm going to say this is PID control, which stands for proportional integral derivative control. What a PID control does is that as your error input changes, the higher the error, it adds a certain amount of control given by the proportional gain. And as the rate of change of error changes, it adds some amount of control that tackles the change in the derivative of the error. And then the last one that gets added is that it looks at the entire history of error over time. Starting from time t0 up until some time t, it looks at what is the culmination of error that has led up until this point, and it tries to tackle that by adding some amount of control to it called as integral control. So the advantage of the PID control is that higher the error, it generates a higher gain given by Kp. The more rapidly your error changes with time, then it adds a derivative control Kd to tackle that. And it also looks at the time history of all the errors in your system from time t0 to some time t. So as long as there is some error in your system, some amount of control is always provided in order to tackle this error. So the biggest advantage of a PID control system is that you are eliminating the case of a steady state error. So if you want an aircraft to pitch by 5 degrees and the aircraft is at 4.99, you constantly have some control that's looking at the history of error over time that's going to minimize this error. So biggest advantage of a PID control is that it'll eliminate the steady state error in our system. Or in other words, this is a controller that achieves precise control. If you provide a reference input of 5 degrees, then your system will settle at 5 degrees because you have a controller now that tackles how much your error is present in the signal and how fast your error changes with time, along with looking at the history of error in your system. All right. But one downside of a PID controller, which we will discuss in the next lecture, is that it needs some amount of tuning. You have to figure out what is a good amount of the Kp, Kd, and the Ki values for the gain you want to set into your system. And this requires some trial and error. There are some advanced methods to train to tune your PID controller to have the most optimal sense of control based on the amount of overshoot you're willing to accept, the amount of time you're willing to accept for your system to settle in your final state. But we'll talk about that in the next class. A good application of the PID controller is for typical flight systems. All aircraft and spacecraft systems use PID controllers. While there are more advanced controllers that aircraft and spacecraft systems do. A simple quadcopter or a simple attitude control of a spacecraft, they all use PID controller because they're cheap, readily available, and for specific controls like a quadcopter or the attitude control of the spacecraft, there's enough study that's done that gives you some amount of direction for tuning the controller. So tuning doesn't really become a big problem, and we eliminate the complete steady state error, or in other terms, we achieve precise control. So this is the type of controller that's usually preferred. And now Talking about why PID controller or how the PID controller actually tackles this error, let's consider a simple example. Let us assume we have a spacecraft which is operated by some amount of torque, which I'm going to call TD, and this causes the attitude of the aircraft to change, the spacecraft to change. Say, for example, this results in some amount of angular velocity. Then from Euler's equation, we know that in such a case, the output is given by where we have I'm just going to call output y dot is dependent on the amount of torque that's present in the system, assuming we have principal axis. All right. Then for this, let's go ahead and add PD control. All right. Then in such a case, the output of the system I y double dot is given by some amount of Kp, which is the Kp times the error. Error here is basically how the reference signal R changes with time minus what the output of the signal is at that time value. So we have Kp times R minus Y. Um, my plus, let's say we have some Kd value. Let's assume this is negative Kd times this changes as the rate of change of output, so this changes with y dot of t plus the torque that we applied, Td. All right, now let's consider a case when y dot is equal to 0. If y dot is equal to 0, then naturally y double dot becomes 0. Substituting this into this equation, we get 0 is equal to Kp times R of t, which is the reference, minus y of t, which is our output, minus Kd times 0 plus Td. Or in other case, when the system is not changing with time, which means the state of the system is constant, which is y dot of t is equal to 0 and y double dot of t is equal to 0, then even in such a case, we have some amount of error, which is E of t is given by R of t minus y of t, and this amount of error is given by this equation Td by Kp. Or in other cases, even if your system state is not changing with time, there is some amount of error present in the system, which is given by TD and KP. Or in other words, your system you desire a response of say 1 degree, and your system has now settled somewhere based on the control. It is settled at somewhere, instead of 1 degree, it's let's say settled at 0.9 degree. Then you basically have this amount of error always present in your system, never leaving. So what the PID controller does is that it looks at the total area under the curve, which is the summation of all the errors. Here area is given by 0 to t, e time E of t dt, and PID controller adds an integral term which we said is given by Ki. This Ki we say has memory because Ki looks at the area under the curve, or it looks at the total amount of error that is being accumulated in the system as a function of time, and it tries to eliminate that by adding some corresponding Ki to drive the error to 0, to drive E of t to go to 0. All right. Now let's move on to the final segment of today's lecture, in which we're going to talk about block diagram. So far, what we've discussed is that we've looked at different second order systems. We've looked at what each of these second order systems transfer function look like, and then we also looked at the time response of the system, where we said based on the input that we provide, the system takes some amount of time before it settles down into a final steady state value. Then we defined a bunch of parameters called as the rise time, peak time, maximum overshoot, and settling time. And then we also looked at the final value theorem, which talks about what the steady state of the system would be if the system has one pole on the origin and the other poles are always on the left hand side of the j omega axis. And then we also now looked at some common types of control. Now, if you notice, typically when we were analyzing each of the behaviors of these systems, they're all dependent on time. And they're usually given as a set of differential equations that you need to solve for. One way we eliminated the need for solving these differential equations is we converted them into Laplace domain, where now all the differential equation integration and differentiations got converted into algebraic quantities, where you're just performing multiplication, subtraction, addition instead of integrating equations or differentiating them with time. But still, these equations tend to be complex, where we looked at some of these examples as we add different amounts of control inputs. So one way people have identified to simplify this whole process, understand the dynamics of the system, and also come up with efficient ways of designing control is to represent each of the component of the system as a block. Here, basically, each block represents a differential equations, or it could represent an algebraic equation that talks about what the dynamics of the system are based on different inputs. And as we represent different blocks, and then we're going to take each of these equations and then convert them into Laplace domain. Once we convert to Laplace domain, we know that the system uh, uh, has now been converted from differential equations to a set of algebraic equations. And we know for algebraic equation operations, we can just add and subtract. So now we're going to look at how we can simplify our understanding on the dynamics of the system by breaking down the dynamics of each component and then adding blocks, subtracting blocks, combining blocks, all to give us the final response of the system. Or, in other words, what we're trying to do here is that we are trying to represent the entire system's dynamics, which includes specific dynamics of each of its component, and combine them into one single transfer function. All right. Or in other words, we're going to look at how we can represent the system in terms of blocks and how we can simplify these blocks. Typical to any system, you have some amount of input called as the reference input R of S. This is the desired state for the system, and you have the output of the system given by Y of S. Then, how the input for the system gets converted to the output depends on the dynamics of the system, which is usually represented by this quantity G of S, which we called as the transfer function of the system. We said the transfer function Gs is nothing but Y of S by R of S, which is basically the output divided by the input, where the input and the output are represented in Laplace domain. All right. Or rearranging this equation, we can say the output Y of S is nothing but some gain G of S times the reference input R of S. All right. Now, we also looked at control systems where we said for the given dynamics of the system given by G of S, we wanted to add some amount of control input. Here, in the previous case, we called it D of S. Here, I'm just assuming we have another block H of S. Or in other words, if two components of the systems are connected in series, then what is their uh, essential transfer function? Here in this case, the transfer function TF is given by Y of S divided by G of S. Here, let's break it down into each blocks. You have R of S, which gets multiplied by H of S. So here you have H of S times R of S. And then this now becomes an input to the G of S blocks that gets multiplied by G of S. So you have H of S, G of S times R of S, which goes into your output. So our output here, Y of S, I'm going to erase this. Then our output here, Y of S is given by H of S times G of S times R of S. We said our transfer function is nothing but our output divided by input. Then in this case, the transfer function is nothing but the product of the two terms that were connected in series. H of S times G of S. Let me rewrite this to increase clarity. It's H of S times G of S. So if two blocks of the system are connected in series, then we can simply multiply them. Now, what happens if two blocks of the system are connected in parallel? Then here, analyzing this point, which we're going to call it as break off point, Then we say the signal that goes in here is still R of S. The signal that goes here is R of S. Then here the output is G of S times R of S. And here the output is H of S times R of S. And then these two gets combined into a block, which we call as summation block. Then the final output Y of S is given by G of S times R of S plus H of S times R of S. Taking R of S common, we can write the output Y of S is nothing but G of S plus H of S whole thing multiplied by R of S. Or in this case, the transfer function Y of S divided by R of S is nothing but G of S plus H of S. So if two blocks are connected in parallel, then the transfer functions of each of the blocks get added. If two blocks of the system are connected in series, then the transfer function of the two blocks get multiplied. And now let's look at what happens if we have a typical feedback block, and let's analyze the system. Here we have some input R of S, and let's say this goes into some signal B of S, and let's just call this signal A of S that comes back after this block H of S. Then can I say this block A of S is nothing but H of S times my output Y of S, because this is where I have my output. A of S is nothing but H of S times Y of S. And looking at the same block, can I say B of S is nothing but the nothing but the input signal that goes here, which is which I'm going to say is the amount of control input that goes into the signal. I'm going to call that control input U of S minus, sorry, I called it R, right? So can I say that this B of S is nothing but R of S minus A of S? Correct. And looking at the same block, can I say my Y of S is nothing but B of S times G of S? Now what I'm going to do is substitute for B of S using this equation and then substitute for A of S using this equation. When I do that, I get Y of S is equal to G of S times R of S minus A of S. This is G of S times R of S minus H of S, Y of S. This is nothing but G of S times R of S minus G of S times H of S times Y of S. And simplifying this equation, I have Y of S on one side and then I have Y of S on the other side. Rearranging this equation, I end up getting Y of S times 1 plus G of S H of S is equal to G of S R of S. Or rewriting this equation, I get Y of S by R of S is nothing but G of S divided by 1 plus H of S G of S. Or the transfer function for a feedback block that looks as shown here is given by the gain G in the numerator divided by 1 plus gain G times the gain H. All right. Now let's look at a simple example to see how this simplifies the essential block diagram. Or in other terms, I have a simple feedback signal where the plant is given by G of S has 1 by S plus 10, and then we have H of S given by 1 by 1 plus S. Then if I want to simplify this into a simple block, then I can say the reference input R of S is nothing but some function. I'm going to call this G star of S takes me to my output Y of S. Then from this equation, using this equation, I can say My y of s by r of s is g star of s. This is given by g of s by 1 plus h of s, g of s. In this case, g star of s is nothing but 1 by s plus 10 divided by 1 plus 1 by s plus 10 times 1 by s plus 1. Or simplifying this, I get g star of s is s plus 1 divided by s squared plus 11s plus 11. This is representing this in the standard form. All right. Now let's look at a few ways in which we can simplify a block diagram. And let us say I have some input u1 that I provide to the that I provide to my system, and this gets multiplied by some gain. I'm going to call it g1. All right. And this goes to form the output I'm going to call y1. And the u of s or u of 1 directly goes to some output y2. Then if I want to move this pickoff point here to a point after the gain, then u of 1 is essentially some block g1 times here we have y1, and then here we have another block which is 1 by g1 goes to y2. Why? Because y1 in this case is nothing but u1 g1 and y2 is nothing but u1. Now let's look at this block. In this block we have u1 times g1. So the signal here is u1 g1 which goes to y1, and then you multiply that here by u1 g1 divided by g1 which goes to y2, which is nothing but u1. So simplifying that, I'm going to write y2 is nothing but u1, y1 is g1 u1. In this case, y1 is g1 u1 and y2 is u1 g1 times, because they're connected in series, we multiply them, times 1 by g1. This is nothing but u1. So these two are equivalent. Okay, I'm going to say moving break point. All right. Now let us say I have another feedback where the input is given by R1, and here I have a feedback block plus and minus, and here I have the gain G1, and then I have my output Y1, and then in the feedback block, let's say I have some gain G2. Now, if I want to move the feedback block, this is the same as me saying I have some R1 times 1 by G1. I have the summation sigma plus, here I have minus, this is G2 times G1 Y. Essentially what I have done is I have taken this feedback block and I've taken the feedback block and I've completely moved it towards the numerator. All right. To do that, I have to pre-multiply the entire input by the gain 1 by g1. Let's check if these are equivalent. Here we know for a typical feedback, the total transfer function is nothing but g1 divided by 1 plus g1 g2. Let us verify if it is the same. In this case, let me write that y1 by r1. Then in this case, let us see if this is the same. We have y1 by r1 is nothing but here I have some input which is R1 by G1, and then this goes into the feedback. This whole feedback block, here we have two things connected in series, and then in the feedback you have nothing, which means you have unity feedback. Then that can be written as um, sorry, this needs to be G2. Then this can be written as 1 by G2 times some other block here, and this block is given by a unity feedback here, while we have two product terms in the numerator, where the transfer function here is G1 G2 divided by 1 plus G1 G2, and simplifying this we get Y1 by R1 is nothing but G1 by G1 G2 plus 1, which is the same as the one on left side. Which means if you have a feedback gain that you want to send back towards you want to send back here to this block, then you have to pre-multiply the entire system by 1 by 1 divided by that gain. And now let's look at another system. Let's say I have two inputs, U1 and U2, and then these two get combined into a summation to form the output. Let's say this is plus and minus, and this goes to again G1. This is as good as saying that this block can be represented as U1 multiplied by gain G1 goes to the summation, and then we have U2 multiplied by gain G1 and then goes to the summation all the way to Y1. So here what I'm doing is here I'm basically taking this summation block and I'm moving it to a point after the gain. Then in such a case, the block diagram gets simplified by this. Let's make sure that this is still valid. In the first case, we have y1 is nothing but u1 minus u2 times g1 in this case. And here we have y1 is u1 g1 minus u2 g1, or y1 is u1 minus u2 times g1. So these two are equivalent systems. All right. Awesome. 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 We've covered a few basic block diagram geometries. Now let's look at a quick example. Let us say I have a block diagram here. My input R of S gets into a summation. Here, let's say it's plus, and here minus. And we want this. I'm going to write it below, so I'm going to erase it here just so I have more space. So I have an R of S that goes into a summation block. We have plus, and then we have a minus here. This goes through a gain I'm going to call G1. And then this has another summation block here. Here, both times it is plus. This goes to a gain G2. And then this goes to a gain H2 here on the feedback side. And then here we have another summation sigma, which takes a signal from here and goes all the way here, adds both of these signals, and then this goes towards the output y of s. And then we have a feedback from here, which goes into a system where we have a summation, we have plus, and then here we have another plus. Let's say this goes through a gain G3, and then this comes all the way back here. But then we're taking some part of feedback where we say we have H3 that goes here. All right. The idea now is to simplify this entire block diagram and write it as one single block diagram. Okay? To do that, let us start by just considering this block. Okay? Let's just look at this block where we have something that looks like a feedback system. And then let us look at this block where again we said it looks like a feedback system. We know that for a typical feedback system, the gain is given by G1 divided by 1 plus G1, G2. Notice here it had a negative sign, while if we go back here, both of them have a positive sign, which means to say if this is positive here instead of negative, then in the denominator we'll have a negative here instead of the positive. All right. So now just simplifying these two transfer functions, let's call this transfer function as G2 star, and I'm going to call this transfer function as G3 star. All right. Now I'm going to write expressions for G2 and G3 using the transfer function block. So just looking at G2 star, which is basically we have sigma, we have G2, and then we have plus plus, and then here we have H2. Simplifying this block, I can say the transfer function G2 star here is nothing but G2 divided by 1 minus G2 H2. And similarly, let's look at G G3 star. G3 star is basically this block where we have G3, we have H3, and then we have a summation, we have a plus, plus. This also looks like a typical feedback loop here, except in the feedback loop, the direction is just reversed. So we can still simplify this as G3 star is nothing but G3 divided by 1 minus G3 H3. So we've looked at two different blocks. We've simplified what each of their transfer function are. Now taking these two blocks, let's write a new block diagram for the system. Here then we have starting from R of S. It goes all the way to sigma, where originally we had a plus, we had a minus here. This goes through a block G1. G1 then goes to a block, we called it G2 star, and then this goes into a summation point sigma, and then we had a signal going here, and then this led to the output y of s, and then a part of the output was coming back to the input through another block which we called G3 star. All right, now what we're going to do is we're going to look at this system here, and we're going to simplify this system here. This is called as a feed forward system where you're taking two inputs and then you're combining them here. So this is as good as a system where let's call this system as gain. Let's call this G2 double star. And then I'm going to write what G2 double star here is. Then G2 double star is nothing but a system where we have two gains. Here this is G2 star, versus if we have nothing, it's as good as a gain of plus 1, and then these two get added here. Now this looks as if we have two different gains that are getting added here to the signal. So the simplification of this is that we have G2 double star is nothing but 1 plus G2 star. All right. Now I'm going to substitute that into the block diagram where we have R of S, which originally goes through the summation. We have a plus, we have a minus here. This goes through a block G1, which in turn goes through a block which we call G2 double star. And this goes to the output Y of S. And then from here, we have some amount of feedback. And here in the feedback, we called it G3 star. That goes here. Now I think you guys already expect what I'm going to do next. I'm going to take this block. I'm going to simplify this. I'm going to call this block as G2 triple star. All right. Then G2 triple star is nothing but some gain G1, and then we have some gain G2 double star. These are basically two gains connected in series. Then in such a case, we said the effective transfer function is nothing but the product of those two. So G2 double star is nothing but G1 times G2 double star. And now substituting that into this block diagram, what we essentially get is that we get this block where we have my input signal R of S. This goes through a summation, we have a plus, and then here we have a minus. This goes to a block which we called G2 triple star all the way to the output Y of S. And here in the feedback, we have something called as G3 star, which was going back here. Now looking at this system looks like a simple feedback system where we have plus and minus. Here in this case, the transfer function is given by Y of S by R of S is nothing but G2 triple star divided by 1 plus G2 triple star times G3 star. Then this reduces the transfer function to R of S is nothing but some gain times Y of S. Let's assume that I'm going to call this whole feedback block as G. Then here the gain G is given by this value that we just discussed. Here the total gain G is given by this. Then simplifying all of this math and substituting all of the equations, we can say the gain G is nothing but, let me write it here to give us some more space. The gain G is nothing but G2 triple star divided by 1 plus G2 triple star times G3 star, which is substituting for all of those values, we get G1 times 1 plus G2 divided by 1 minus G2H2, this in the numerator, divided by 1 plus G1 times 1 plus G2 divided by 1 minus G2H2 times G3 divided by 1 minus G3H3. Basically, I'm substituting for all G2 star, G2 double star, G2 triple star, and G3 star. Then substituting this, we can write the total gain equation here to be given by G1 times 1 minus G3H3 times G2 plus 1 minus G2H2 divided by 1 minus G2H2 into 1 minus G3H3 plus G1 times G2 minus 1 minus G2H2. This will be the simplified transfer function. So now we have taken a complex system and then we have reduced the entire transfer function into one equation that is represented as a simple numerator and denominator, both represented by a polynomial. So this is a good way we can reduce transfer functions. We'll also do another example in the next lecture, and then we'll finally move towards some more details on solving numerical problems using block diagram simplification and analyzing what the overshoot is, what is the rise time, fall time, peak time, and then looking at all all of this, let us look at how do we now design the values for G1, G2, H1, H2, H3 such that the system's characteristics are what we desire. So the whole idea of this block diagram is that now you can fine tune what each of the values for G1, G2, H1, H2, H3, which can be different amounts of controls for each subsystem on your entire system, which might be an aircraft or a spacecraft, and how all of this plays into some desired characteristics that you are looking for. So in essence, you could take the same knowledge, apply it to a complete aircraft system where you have one system that controls the ailerons, one that controls the rudder, and one that controls the elevators, and comparing all of these and then trying to figure out how much of control can we add or tune into each of these to get desired aircraft dynamical characteristics. All right, awesome. I'll see you guys next class.